Hello everybody, I'm trying something a little bit different here today. Instead of doing my typical iPad recording where I prop it up kind of haphazardly and walk and point in front of the board, I've decided to sit down directly in front of the board and try and use this fancy little zoom feature on my phone to try and actually do some recording here. But anyway, first thing we want to consider today is that we're trying to relate our molar specific heats C sub V and C sub P, right? So that's kind of the goal of today. And what we can do in order to do so is that we can actually make use of some of the derivations we did previously with our our Maxwell relations. Somebody likes driving. Anyway, we start off with some really simple definitions for our heat capacities, being that capital C sub V is equal to our change in heat with respect to temperature with a constant volume, and a change in temperature, a change in entropy with respect to temperature at a constant volume. And the same thing with our specific heat, or our heat capacity at constant pressure, except we take our partial derivative of our entropy with a constant pressure instead. So since we have easily controllable external parameters in our temperature and in our pressure, what we can do is that we can let those be our independent variables for this particular calculation, right? So we can essentially expand our ds term for our entropy in our equation for a change in heat, dq. And the way we do that is typically, with our standard definition of a differential, where you take the partial derivative of your function with respect to one of its variables, and you multiply it by some infinitesimal change in that variable, and you add onto it the partial derivative of your function with respect to the other variable times the infinitesimal change in that other variable. So in this case, you would have a partial derivative with respect to entropy of temperature times dt par s par p dp, right? That's what we get. And dq here specifically is an infinitesimal amount of heat that gets absorbed in some quasi-static process, right? Moreover, we can write dq as be in terms of its heat capacity with constant pressure by expanding out that TDS term. I think with the second law is where that would come from off the top of my head. But basically you get that dq is equal to our heat capacity with constant pressure times dt plus that partial derivative term of our entropy with respect to pressure at a constant pressure times dp times t. Now the fun thing about dp here is that we can try and expand it out in terms of temperature and volume, because those are our controlled external parameters. And when we do that, we get this kind of ugly expression right here with the temperature times the partial of s with respect to pressure times the quantity of the partial of pressure with respect to temperature plus the partial of pressure with respect to volume. Now, for a quasi-static, I believe, or at a constant volume, we know that dV has to be equal to 0. So we can get rid of that second term in the big parentheses. And then we can just write that our change in heat, dq, is equal to our heat capacity, Cp, times some infinitesimal change in heat, dt, plus T times our partial of entropy with respect to pressure, and our partial of pressure with respect to temperature, times some small change dt. Now, we know that if we divide both sides of this equation by dt, we will recover our heat capacity at a constant volume up here, because that's what we defined it as at the very beginning, after all, right? So with that in mind, we do have an equation with respect to our specific heats and how they're related to each other with entropy and pressure and temperature. However, that doesn't tell us about how to express this in terms of volume and whatnot. So in order to amend that, we have to make note of our Maxwell relation. this particular Maxwell relation, where we have a partial of our entropy with respect to pressure is equal to our negative partial of V with respect to temperature. And with that, we can also introduce another term, A sub V, or alpha sub V, which is our volume coefficient of expansion. And our volume coefficient of expansion is defined as 1 over the volume times the partial derivative of our volume with respect to temperature at a constant pressure. With that, obviously, we can move some constants around. We could say that that partial derivative with respect to V is equal to our volume times our coefficient of expansion. And by extension, with that Maxwell relation, we can relate that back to our partial with respect to entropy. Now that we have that, we can also look at our change in volume over some small amount of pressure and temperature. But once again, we know that for constant volume, dV is equal to 0. And we can also make that same substitution we did earlier with our dP term and cancel out that other dV term, which leaves us with this following expression equal to 0, where we have a partial derivative of our volume with respect to temperature plus the product of our partials of V and P with respect to pressure and temperature respectively. If we move some terms around and isolate dP dt, we get that it's equal to the negative partial of the volume with respect to temperature divided by the partial of the volume with respect to pressure at a constant temperature. At this point, it would be handy to introduce another handy measurable quantity known as the isothermal compressionability constant, K sub T, which we just simply define as 1 over the volume times our partial of our volume with respect to pressure at constant temperature, right? So with that in mind, we can just completely and totally make some substitutions here and rewrite that our partial with respect to P with respect to V. I did not write that correctly here. Let me actually correct that while I'm sitting here. Doop-a-doop-a-doop-a-doo. There we go. That's why I normally like to have it stable so it doesn't go crazy when I'm trying to record. Anyway, with that in mind, what we have is a simple substitution where we can substitute back into our expression for our specific heats after getting them on the same side of the equation on the left there. And when we make our substitutions for this value and this value up here, just drag and drop them in there, we get that our difference between the specific heats with respect to constant volume and constant pressure constitutes a quantity of our volume times our temperature times the coefficient of volume expansion squared times our KT, being our isothermal compressibility. Now, we can also write this in terms of our molar specific masses, and all we have to do is make note that our the number of moles of the system there can be related to the volume and the number of moles in our system, and we just make that simple little substitution that we have made in the past. So I think that'd be like volume, so big V divided by nu, plug that in there, and then you can get that expression. Anyway, and then Fitzpatrick concludes this particular section with an example where he takes the ideal gas law and then he makes some small change in our volume, and then he makes note that if we take a partial derivative with respect to the volume itself with respect to temperature, we get the expression of nu times R divided by P, which is just equal to the volume divided by T at that point. And then we also make note of the fact of what our volume of coefficient of expansion is equal to in this case. When we divide both sides by 1 over V, we see that that is equal to 1 over T by direct comparison. At a constant temperature, we also note this particular differential where we have PdV plus VdP is equal to 0. We look at our partial derivative of the volume with respect to the pressure. We note that that gives us a quantity of negative V over P. And then when we move some terms around once again with some simple algebra, we can relate that to our isothermal compressibility, and that ends up being 1 over P. And then last but not least, we know that our moles per, our volume per mole quantity little v is equal to big V divided by nu, which is equal to the gas constant R times T divided by the pressure. And then what we do is that once we know these particular values, we can substitute them back into this quantity here. And sorry for my chicken scratch here, my small pen kind of died and I'm dealing with a big old wedge pen. We just substitute those terms back in there. The terms cancel out very nicely and very cleanly. And we are left with just R. Let me actually rewrite that because that's like ugly as sin. My heavens. Didn't realize that until I was recording. This is equal to, it's kind of hard to write down like here. I'm just kind of tall. Anyway, that gives us back our gas constant R. But ultimately, all that shows is that Cp minus Cv is equal to R. That was the main point of doing that particular example with the ideal gas law. No, but yeah, all in all, that's section 6.13 in Fitzpatrick, and that is how you relate our specific heats together using our Maxwell relation and some simple knowledge pertaining to the differential behaviors of quantities mathematically, and moreover relating those things to actual measurable quantities like our volume of coefficient of expansion and our isothermal compressibility. I hope this was a handy video and that it was enjoyable. I think because this was kind of a one-off deal, I'm not really going to go back to doing this again too often, but yeah, I think I might stick with the iPad. Let me know what you guys think. If you like me being able to go, woo, you know, do let me know. Anyway, have a good one.